Okay, for chapter 15, we have a few words about laws of thermodynamics. Of course, the discussion of those laws is going to take way more than just a single chapter. This is just a brief introduction to the first and the second law. And uh, there's like a whole textbook that you can read about the laws of thermodynamics on its own. So, just a brief introduction and a little discussion, and we can see what we can do with that. Solve some problems after this. Um, so first of all, you can see that there's a big difference between what we defined as work done for mechanics and what we are about to define for work done in thermodynamics. So it was the energy transfer to or from the system. And that's what we said that was work done. Work done is positive. Energy is transferred to the system, or negative, then the system loses energy. It's not the case anymore. For thermodynamics, you cannot say that work is energy and energy is work. We have the third thing. We have the heat. We define the heat as the transfer of energy due to the change in temperature in chapter 14. And you can see that heat is not work. You can't say that that energy transfer that you define heat with is work. It's not that anymore. So work in thermodynamics is a transfer of energy, but that's not due to temperature difference. This is the big deal. That's what we have to understand right away. And it's a big difference between the mechanics and thermodynamics. So transfer of energy, that is not due to a temperature difference. So let's see how the conservation principle looks like, because the first law of thermodynamics is pretty much the conservation of energy principle. And there was kinetic energy, potential energy for mechanics. Now let's see what we have for thermodynamics. Here it is. First of all, the system must be closed. So it's only for a closed system, and that means that mass doesn't enter or leave the system. You have the change in internal energy. This is your change in temperature and everything that you calculate with. And the energy within the system uh, is, uh, you might say, a sum, you might say a difference. That really depends on how you treat the work done. Some textbook would say plus work, some textbook would say minus work. Uh, this expression says minus, but work done by the system is not the same as work done on the system. So you have to pay attention to the definitions and what kind of work do we have. Is it the work done by the system or on the system? So change in internal energy on one side, heat, this is your energy added to the system. We defined heat before. And you take away the work done by the system. So you might say plus work done on the system or minus the work done by the system. Um, so still positive or negative heat. That means you gain heat or you lose heat. So you have options here. So Q can be positive or negative. And then work done also has options. If it's work done by the system on the environment, on the surroundings, then it's a positive value. If it's the work done on the system, then it's negative. So Q can be positive or negative, your heat can be positive or negative, or the work done can be positive or negative, and depending on this little add on to the word work, you have to be careful and do the calculations correct. So three things. Anything is possible. You can get positive, negative, or zero for delta U for the change in internal energy. You can get positive, negative, or zero for the heat. And you can get positive, negative, or zero for the work done. And we're about to discuss a few processes, and you'll see how the first law of thermodynamics works for all of those processes. So positive, negative, positive, negative. You have to keep that in mind and read the problem carefully before rushing to the law and start doing Q minus W. That Q might be negative and the W might be positive. You have options here. So here's a little example. Let's see, we have 3,000 joules added to the system, and 2,000 joules of work is done on the system. Do you see the difference? It says on the system versus what we defined as by the system. So the trick is to realize that if it's by the system with a negative, then on the system, you will do the opposite of that. So essentially, so here's the answer. Check it out. Your work done on the system is opposite to the work done by the system, and that's why you have the extra negative sign. So instead of subtracting 2,000 joules, you might say, oh, it's just 3,000, take away 2,000, end of story. No, the 2,000 must be added because you're effectively taking away the opposite of what is the work done by the system. So taking away a negative, that's adding, and instead of 3,000 minus 2,000, you have 3,000 plus 2,000, and that gives you 5 kilojoules. Once again, pay attention to if it's on the system or by the system, if it's added to the system or removed from the system. That would be the difference for your first law of thermodynamics calculations. Okay, so here we go with few processes, the simplest setups, and you have to assume equilibrium throughout all processes, so we don't have, we only care about the initial and the final conditions. We don't care how the system changes from A to B. And the first process is isothermal. And it speaks for itself. The name speaks for itself. Iso means equal, and thermal means, temperature. So it's same temperature for the initial and the final state. So at point A and point B, you have the same temperatures. So if temperature is constant, then the ideal gas law, which is PV is nRT, T is constant, R is the universal gas constant, so it's also constant, and N is concentration, also constant. You have PV equals constant. So pressure times the volume is a constant value. Now for your PV diagram, if pressure goes up, then volume must go down so that the whole product is constant. If pressure goes down, then volume must go up. Once again, to keep it constant. So for isothermal process, your PV diagram has a graph of a hyperbola. It's the inverse relationship. So greater pressure, lower volume. And if you're going this way, then it's less of a pressure and greater volumes. So let's see what the first law will give us if change in temperature is zero. So constant means there's no change. It's not necessarily zero, but the change in temperature is definitely zero. So it is 5, it was 5, 5 take away 5 is 0. It was 50, now it's 50, 50 take away 50 is still 0. So the change in uh, internal energy, which depends on delta T, if delta T is 0, then change in internal energy is also 0. And that means that for your first law, if delta U is 0, transfer W, the work done on the other side, and it's Q equals W. That's what you're going to get in this case. So the heat is the same as the work done uh, the work done by the system. So by the system, not on the system. Next process is isobaric. Remember that bar is a unit of pressure. We have pascals, of course, but you can also measure them in bars. And isobaric, iso is equal, is the same. So same pressure. That's exactly what isobaric process means. And that means change in pressure is 0. The pressure by itself is not necessarily 0. Pressure can be any number, but the change in pressure is 0. Final takeaway initial, there's no change. So for the ideal gas law, PV and RT, you have P as a constant. So you divide both sides by temperature and you get volume over temperature is constant. So for PV diagram, what kind of a graph do we expect? Well, it's going to be a horizontal line. You can see the pressure at point A, same as the pressure at point B. The graph is called isobar. And let's see what we get for the first law of thermodynamics. First of all, what is the work done? Yeah, work done is force dot displacement, force times displacement times the cosine of angle between the two. And what kind of a force are we talking about? It's your pressure times the surface area for those pistons that are expanding or compressing the gas. So for constant pressure, your work done is just the pressure and A times D, surface area times the displacement times the height is the volume. So change in volume times the pressure. This is the work done by the expanding gas. So last process is isovolumetric. Iso is the same, like equal, and volumetric is the volume. So volume is constant. That's the definition. Constant doesn't mean 0, but the change is definitely 0. And for your PV equals nRT, divide both sides by the temperature. And keeping the volume constant, you have the ratio of pressure to temperature being constant. Let's take a look at the diagram. It's called isocore. And same volume. So volume at point A is the same as the volume at point B. What kind of a work done are we talking about? If work done is pressure times the change in volume, and change in volume is 0, then something multiplied by 0, it's 0. So this is your property for isovolumetric process. Volume doesn't change. That means work done is 0. There is no change in volume. Multiply the 0 by any pressure, the work done is 0, and the first law automatically becomes a little shorter. Your delta U is not Q take away W. The W is just 0. The work done is 0. So your change in internal energy is completely dependent on the energy added to the system. So W is 0. And the first law looks like that. Should make sense. So isobaric, isovolumetric. Sometimes you'd say isochoric. Isochore is the graph, so isochoric process. Yeah, one more process, which is a special one. It's not an iso process. It's not isovolumetric, isobaric, or isothermal. It's adiabatic. What's so special about adiabatic? There is no heat added to the system or removed from the system. So it's the case when the Q is zero. You can think about an extremely well insulated system. Of course, it's not possible. There's always going to be some heat loss. Uh, some heat will try to run away from the system. But let's pretend we have a very well insulated system and we can consider the Q being almost zero. So if this is the case, then Q is zero and change in internal energy is just the negative of the work done. Be careful, by the system. We're still talking about the definition of the by the system. Once again, some other textbooks might say work done on the system, and instead of a minus, you will get a plus then. Okay. Yeah, and you can see that adiabatic process as on the diagram. It's kind of isothermal, but it's a little different. It's a little steeper than isothermal. So do not confuse isothermal with an adiabatic graph. So yeah, how do you calculate the work done if you have multiple processes? It's very simple. It's the area under the PV curve. Work done is P times the pressure times the change in volume. So if it's PV diagram, everything below the curve would give you the area. The area below the curve would give you the work done. So A to B, you would get some kind of something close to a trapezoid. Uh, take away the isobaric here, and you would get the area inside this. It's kind of a triangular shape, but it's not exactly a triangle because isothermal process is a hyperbola. So whatever is inside would be the work done by, say, a heat machine or a heat engine. We'll discuss that later. So for now, the way you calculate the work done is the area below the PV curve. Okay, one more question. We got an ideal gas that goes isothermal expansion. Okay, so what do we know about isothermal processes? Isothermal process was right here. We say temperature is constant. Temperature doesn't change. That means the change in internal energy is zero. And your heat is work done. So delta U is zero. That means it's either A or B or D. So just because it's isothermal, you say delta U is zero. And then it says expansion. For the expansion, we need the work done. So the volume changes in a way that it gets more, right? So expansion means more volume. So delta V is positive. Pressure is always positive. So it's positive times a positive. Work done is positive. So work done is positive here. Work done is positive there. What's the difference? Oh, no. Work done is positive. Work done is positive. Work done is positive. Okay, so here we go. Delta U is 0, work done is positive. Delta U is 0, work done is negative. B is not good. B is not good. Delta U is positive. No, not good. So it's either A or D. So you got A or D so far when you have those two conditions from what is given as isothermal expansion. Isothermal means delta U is 0, and expansion means work done is positive. So the last question is, what do we have for the heat? Do we have a 0 heat or the heat is greater than 0? You have to remember that Q equals to 0 is a special case when we got adiabatic process. And it's not adiabatic. We don't have adiabatic. We have isothermal expansion. So for isothermal, you have to go with option D, because option A would be adiabatic. Just from the definition of the word adiabatic, you conclude it's not A, because A would be adiabatic, and we got isothermal. That means we have option D. Yeah, and here's the explanation. So delta T is 0. So change in internal temperature, internal energy, excuse me, is 0. And for expansion, that means work done on the surrounding is positive. And your first law gives you this expression. So heat is positive, not 0. Okay, our body does work. And our first law says this. We maintain our constant temperature, which is what, like 90 something Fahrenheit, convert that to Kelvin. And we operate with uh, no change in internal energy. So what is that heat which balances our energy loss? Yeah, this whole story is a trick question, because remember, the first law says what? It's got to be a closed system, right? And closed system means no mass enters or leaves the system. And I'm pretty sure for our bodies, we have a violation of this statement. It's not a closed system, it's an open system, because mass goes in with food and drinks and everything that, has calories, has energy content, chemical energy stored in the food that your body metabolizes in energy. And then there's mass goes out when you go visit a bathroom. So clearly, you cannot operate with the first law for your body, because it's not a closed system. It's a system that allows the mass to enter or leave the system. That's a problem. So this is a trick question. Where is that heat that balances our energy loss? The heat is in the food, but the whole thing is not valid because it's a open system rather than a closed one. Yeah, here we go. That is what it says. Everything is wrong. Bodies are open systems, and it's the chemical potential energy stored in the food that allows us to do some exercise, do some work, and maintain our temperature. Oh, you even have the metabolic rate table. So see, while you're sleeping, you still burn down calories. By the way, don't you say calories? You have to convert to joules for calculations. Uh, we have 1 calorie as 4 joules, and what you consume is actually kilocalories. So well, it's not 2,000 calories that you need per day. It's actually 2 million calories, because they're kilocalories. Okay, on to the second law. So second law has many statements. It's not just a single statement. It's really a statement on its own, which has many variations, many versions. So let's take a look at this case. Uh, have you ever seen that you have a broken cup? One, two, one, two. Sorry, the headset turned off. So you have a broken cup, and all of a sudden, the cup reassembles and becomes just like it was before it fell and broke. I'm pretty sure you've never seen that in real life. And this is the idea of the second law of thermodynamics. We have some processes that can happen, like there is a cup and you accidentally push it and it falls on the ground and breaks. But the reverse process is not possible. So for thermodynamics, you have the same statement. We have the heat that can flow from a hot to cold, but there's no way for the heat to flow from cold to hot. I mean, it can do that, but you have to do work on the system so that this is possible. Your refrigerators and air conditioning units do exactly that. You go against the uh, process, you go against the hot to cold, and you have to pay with energy to be able to force the process in reverse. So some processes happen naturally, hot to cold, and for the reverse processes, you have to do work on the system. You have to input energy into the system, and by doing work on the system, you can reverse those processes, but you have to, pay the price for that. So heat engines, pretty straightforward way. Like I said, it's a natural uh, flow of heat from hot to cold. So once you get a hot uh, reservoir, hot temperature somewhere, it will naturally flow towards the cold. That's the idea for a heat engine. So can we get some work from thermal energy? Yes, we can. Check it out. We got a high temperature reservoir, high temperature area, whatever you call it. And there is a low temperature reservoir somewhere, and it's just natural for the heat to flow from high to low, from hot to cold. And in between, a portion of that energy can be converted into useful work, the work that might, you know, rotate the wheels of a car or the locomotives. If you've seen those steam machines from the past, that's exactly what is going on. So hot reservoir transfers heat to the engine, and a part of it is transformed into uh, work, which may be mechanical work um, for for your use. And the rest is exhausted into the cold reservoir. So you see that we had Q sub H in the beginning, and at the end we have some work being done, and the rest is uh, thrown into the low temperature reservoir. That's the main idea of a heat engine. All quantities are positive. Engines run in repeating cycles, so once you are done with the cycle, your job is to heat up that, say, water back to steam and make it high temperature again and get the work done for the next cycle. Over the cycle, there is no change in internal energy, no change in temperature overall. System returns to the initial state. So here is the steam engine that I was talking about. We start with a boiler. We start with some heat input. You can burn down coal, oil, gas. You can even create a nuclear fission reaction and get that heat input, heating up the water, and some water would eventually become the steam, the gas state for water. And this is your high temperature reservoir. And then there is low temperature reservoir. And what's going to happen naturally, the heat will flow from hot to cold. And on its way from hot to cold, it will expand the piston and force some work being done on the crankshaft or rotating the crankshaft or anything else that you can possibly think of. So some portion of this energy is going to be converted into mechanical work, and the rest would be thrown into what we call the condenser. That steam would be converted back to liquid state, liquid water, and then the pump will pump it back into boiler when you have to heat it up again and continue the cycle over and over again. So basically, you're converting this energy of burning down fossil fuels or fission reaction for nuclear reactor into mechanical work right here in the middle of the journey from hot to cold. So steam passes through, expands the piston, forcing it to move. This is your mechanical energy, the useful energy that you want to get out of this thermal energy. Internal combustion engine, your car engine, if it's not a Tesla, but an old school car, like, I don't know, Honda Civic, Ford Focus, all the internal combustion engines. This is a perfect example of a heat engine as well. You got a chemical energy stored in the gasoline plus some air. So it's like a mixture of gas air. And it is thrown into the chamber. And there is a expansion of the chamber and then compression from the piston. So this is like a setup for what's about to happen next. And at some point, there is a spark that ignites the gasoline air mixture, creating an explosion, like literal explosion. You have a lot of energy released from that explosion. This is your hot reservoir. This is your high temperature that we're going to use to do two things: produce the mechanical work, and the rest is going to be thrown into the exhaust pipe. So the explosion forces the crankshaft to rotate, producing the next cycle of the intake of gas air mixture, and the burned gases, the gases that are left in the chamber are moved to the exhaust pipe. So basically, same idea as the heat engine, but instead of using the steam as your working body and the energy transfer, you just burn down gasoline and you release the chemical energy stored in the gasoline in the form of thermal energy and some mechanical work done. Bad news, the overall efficiency is about 20%. So say the gallon of gas is what, $5? Only $1 out of those $5 would be spent on actually moving the car, propelling the car. The rest is just pretty much heating up the environment. Those exhaust gases pollute the environment and heat up the environment as well. That's the biggest problem with internal combustion engines. You have a lot of energy stored in the gasoline, but you only use 20% at most. So definitely not the best way to use our fossil fuels. Yeah, so with this intro, we have come to the conclusion of efficiency. It's the ratio of the work done, the positive, the work done from the heat machine, like what we need from it, as a ratio to what we've invested into that machine. So how much energy uh, we invested versus what we got out of it. And you can think as work done as the difference between hot and cold. Divide by hot here, and you're going to get 1. Take away the ratio between the heat that was uh, exhausted versus the invested, and you have this little expression for the efficiency. For any heat machine, you can do this. Our power plants, the coal or oil burning coal power plants would give you like 33, 35%, 40 at most. Like there's no way to go beyond 40. And unfortunately, once again, uh, all the energy that we have available in fossil fuels, we're wasting it, and only a third of it would actually be converted to electricity or any mechanical energy you can think of. Very inefficient process. Solar panels, just compare anything to solar panels, that would be 80 to 90% efficiency. Compare that to wind energy. That's the best one. It's like 90 plus uh, percent efficiency. So um, uh, wind and solar is the best way to generate energy and use it. There is very little pollution, and it's very efficient. Okay, the the so-called Carnot engine, the Carnot cycle, is the most efficient you can possibly get out of the thermodynamic processes, the heat machines. It's the isothermal expansion. It's adiabatic expansion. And then you have to go back to the initial state as isothermal compression and adiabatic compression. So A, B, C, D, and back to A. Why is it the most efficient? Because you don't have any losses of energy in between. See, it says adiabatic. Once again, it's very hard to produce adiabatic conditions. There's always going to be some heat lost due to environment around. Even if your system is super duper insulated, you're still going to lose a little bit. So you can't get adiabatic in real life. So this is like an ideal scenario. You can think about it as like no friction scenario. In real life, there's always friction, right? But pretending no friction for mechanical energy. So no losses, no heat losses for thermodynamic uh, machines. This is your ideal scenario. So um, all the engines would be compared to the ideal efficiency, and instead of the heat that we operated for, the formulas right here. So heat to the cold, heat invested, you would switch to temperature. So lowest temperature and lowest and highest temperature. And what's the lowest temperature you can possibly think of? How can you get 100% efficiency? 100% efficiency is when this is 0. Can you get to the absolute 0? Well, theoretically, yes. In real life, no. So you can't really get to the absolute 0 temperature. In terms of Kelvin, of course, we're not talking 0 Celsius or 0 Fahrenheit. It's 0 Kelvin. It's only in Kelvin. And that's why it's ideal scenario. So yeah, the best engines would be 60 to 80% in terms of efficiency, and real engines, real internal combustion engines, that would be like 20, 25%. So very inefficient. And this is from here we get the second expression for the second law of thermodynamics. It's not possible to convert heat into work. There's always going to be some loss of energy in the middle. Yeah, be careful with units. See, it has high temperature of 600, low temperature as 300. You go to the formula and say, okay, uh, 300 over 600, that's what? One half. One take away half, it's zero point 0.5, so 50% efficiency. And it's not. What's the mistake? The mistake is units. Celsius is not the same as Kelvin. Once you convert this to Kelvin, once you convert that to Kelvin, and plug it into the formula for the ideal efficiency for the Carnot cycle, you will see that it's actually not 50, but rather 34. So, yeah. Uh, every time you're doing thermodynamics, do not forget to convert to System International, which is Kelvin, Kelvin only. So when temperature is converted to Kelvin, efficiency is about 34%. Be careful. Okay, now refrigerators, air conditioning, heat pumps, everything is in reverse. As I said before, naturally, it's going to go from hot to cold. And if you want to go back, if you want to go in reverse, if you want to go backwards, you have to pay the price by doing the work on the system. So if you can do the work, then you might force it to in reverse and get that nice cold environment for you to work, study, and everything else. So for a refrigerator, for example, see we have the coils inside. So that would be the collection of the heat from inside. And then there is your compressor motor. And there is a, electric, it's electric device. It's going to consume electric energy, and you'll have to pay for that electric energy eventually. So this is the work done on the system, and your heat from the inside of the refrigerator, it's going to be thrown into the environment. If you ever checked those coils, like the outer on the back side of the refrigerator, you've probably felt uh, the heat coming out of it. That's exactly the process of throwing the heat away and into the environment, away from the inside part. So the heat is collected inside, and then you do the work on producing the high pressure vapor. And with that, all that heat is distributed into the environment. And then there's the expansion valve, which produces low pressure again. So you go back to the initial state. But without the compressor motor, without the electrical energy that you pay for, no profit is going to be there. You will never cool down the refrigerator. So once again, you can see the process is exactly opposite to what we discussed before. So naturally, it's hot to cold, and if you want cold to hot, then you have to uh, introduce some work done uh, on the system. The system, by the way, it's a 1112 tetrafluoroethane. If you ever wonder what kind of a uh, fluid runs inside, uh, it's just chemistry. We're not gonna really go deep into that. What we're gonna discuss is that there's got to be the work done by an electric motor. Otherwise, there is no way for you to collect that heat from inside of the refrigerator and throw it into the environment so that you have a nice cool conditions inside. So yeah, we have a coefficient of performance. This is your efficiency. So we got efficiency for heat engines and coefficient of performance for refrigerator and air conditioning. Plugging back the temperature instead of a heat, you get this ideal, like this is your analog of Carnot engine. Once again, do not forget it's always Kelvin. There is no Celsius, there is no Fahrenheit. You have to convert to Kelvin when calculating temperatures. One last section. It's just a little introduction to entropy. And because we're still discussing second law of thermodynamics, entropy is another parameter that will show you a very specific property for thermodynamic systems. So define entropy as heat added to the system. This is the heat. That's the temperature. And a very cool example that really explains that all right away is what is the change in entropy when you have 50 kilograms of cold water and it's mixed with 50 kilograms of hot water? And hot is 24 degrees. Of course, we're going to convert to Kelvin. And cold is 20 degrees Celsius, also convert to Kelvin. Let's calculate the entropy. So what do we have as entropy for this water and that water, and then we mix them. By the way, if we mix 20 and 24, I'm pretty sure you understand that the average is going to be about 22 degrees. And the amount of heat added to the system, it's the 50 kilograms. Oops, 50 kilograms. 4186 is the table value for water in liquid state. And 2 is the degrees, the delta T. The initial is 20, now it's 22. So we have added this much of energy, this many joules of energy. That is the energy that flows out of the hot and into the cold. So what is the change in entropy? It would be the change for the hot part and the change for the cold part. Let's calculate those two changes. For the hot part, we lose energy, so Q is negative, and that's the amount that we're going to lose. And the average temperature is 23, because it's 22 versus 24. So from 24, we drop to 22. For the hot part, what's the average? The average is 23. And that's the amount of entropy lost by hot. And how much will we get for the cold? First of all, cold receives. It flows into the cold, so it's a positive value. And that's the value. It's once again the 2 degrees difference. But the average for the cold, it's not 23 Celsius, it was 20, now it's 22, so the average is 21. Convert that into Kelvin, and boom, you're getting a value that it's going to be a little more than what we got from the hot. So the hot has lost this much, but the cold has gained more. Not by much. It's only 10 units, 10 joules per Kelvin. But the point is, it's always going to be a positive value. It's always going to be an increase in the overall entropy. So it's hot plus cold, and hot is always going to lose little less than the cold receives. And that's the idea for the second law of thermodynamics. The total entropy, when isolated system, when there is no energy outside transferred in or out, it's always a non-negative value. It's always going to be either zero when there is nothing's going on, or it's always going to be positive. It's always going to increase. So stay the same or increase only. Entropy is not conserved in natural processes, and entropy is also a measure of the disorder, if you want. And there's another statement that you can add to that right away. Everything in this world moves towards a state of greater disorder. Chaos wins. There is no way for that cup of water. Remember the cup of water thing? You gotta agree that this is chaos, right? Those pieces, broken pieces, that's chaos. And that would be the order. Can we get from chaos to order? No, we can't. Can we get from order to chaos? Yes, we can. Very easily. You can break that cup, and then you will never, create that cup again. Even if you start gluing those pieces together, it's not going to be the same cup. So increase in entropy produces increase in chaos. So natural processes tend to move towards a state of greater disorder. Excuse me. Yeah, you can put a milk and sugar in your coffee, stir it. You will get very nice tasting coffee, but there is no way for you to get the milk and sugar uh, back out of um, as natural substances. Like that's it. Once you mix it, there's no way back, and it's going to be just more chaos. Tornado hits a building. It's going to be a lot of damage. You're going to get those building destroyed. Have you ever seen a tornado that would work with a pile of stuff and would leave a building behind? No, it's not possible, right? It's always going to be destruction. Tornado cannot create anything in order. It's only going to create disorder. So, uh, see, there are many expressions that you can think of for second law of thermodynamics. Uh, the idea is you have natural processes, and some processes cannot be reversed, and chaos wins, and so on. You might argue about the growth of individual, evolution in general, like theory of evolution. So is that a violation of second law? No. Remember that we are not closed systems. We already discussed the first law of thermodynamics. You can't apply it to our bodies. Same thing with second law. The second law means isolated system. There is no energy transfer from the environment. So the whole thing, like us being human beings, we evolve because there is, interaction with environment and there is constant exchange with the environment. So it's not an isolated system. Yeah, so eventually all the energy that we have will be converted into thermal energy. Remember friction? We got that kinetic energy, potential energy, and once there is friction, you convert it into heat. Can you recoup that heat and make it mechanical energy again? No, you can't. You can partially convert it into mechanical energy in the heat machine, but you cannot completely convert it back to kinetic or potential. So some of that energy is going to be lost. So this is what we have as a like universe as a whole. Eventually, will experience what we call the heat death. The heat death means all the energy would be converted into thermal energy, and there is no way to convert all that energy back into chemical energy or gravitational potential energy. So this is another implication of the second law of thermodynamics. So yeah, a lot of philosophy behind. There's still a conservation principle, but eventually we have chaos that's going to rule the whole universe. Um, yeah, we got thermal pollution. We have very inefficient engines. It's good that we are trying to switch from internal combustion engines to electric engines. We need solar panels. You know that we need oil to build those solar panels from, right? So we would rather build solar panels and make it very efficient, like 80-90% efficient, rather than just burn down oil and get 20-25% efficiency out of this burning process. So switch to uh, wind and solar. That's the best way to make it sustainable. Yeah, with that burning down of carbon dioxide and other greenhouse gases, we got global warming. Global warming is real, no matter what politicians say. We're clearly rising the average temperatures on the Earth, and that's not good for climate change. Okay, some more uh, tips for problem solving. Be careful with the signs. Yeah. So like I said, remember that delta U equals Q minus W. It's only minus because it's only minus. Where is it? Definition. It's only minus because it's by the system, right? If it's on the system, you should think a plus. Q, it's not always a plus Q. It can be minus because if it's energy added, yeah, it's positive. If it's energy removed, you will see a minus here. So be careful with plus and minus. Be careful about units. Remember the temperature must be in Kelvin. There's no way to do Celsius or Fahrenheit. Forget Fahrenheit, forget Celsius. It's only Kelvin. Otherwise, you'll make mistakes like we discussed for the efficiency of 50% versus 34%. Efficiency is always less than one. If you ever find an efficiency of one, you just violated the second law of thermodynamics. Don't do that. And entropy increases. If your entropy decreases, you're going to be violating the second law of thermodynamics. It's like, can a person jog at 100 miles an hour, right? It can't. Like a person cannot go that fast. Yeah, efficiency cannot be one or greater than one. It's a violation of laws of thermodynamics. Yeah, joke of the day. Yeah, positive proof of global warming. And yeah, that's the end of chapter 15. Up next, well, it's going to be electricity and magnetism. Let's stop the recording.